Okay, let's dive right into this explainer. If you're used to testing traditional software, your gut instinct is probably to treat AI exactly the same way, right? You put in an input, you expect a specific output, and you give it a pass or a fail. Makes total sense. But today, we're going to break that habit entirely. We're moving completely away from those simple pass/fail checks, and instead, we're going to learn how to intentionally map a system's brittleness. By the end of this quick 7-minute deep dive, you're going to be thinking like a true AI test designer. So, we've got to kick things off with a pretty crucial question. Are you actually testing a system, or are you just admiring a lucky output? I ask this because it shatters a really common illusion we see all the time in the tech world. Look, just because an AI spits out one flawless, beautiful response, that doesn't mean the entire system is high quality. It's literally one of the biggest traps in AI evaluation, mistaking a single good sample for a consistently solid system. A model can look absolutely brilliant on a handful of prompts, but then totally faceplant the second the topic shifts or a user gets a little confusing. Just think about the difference here. Traditional software is basically like a fixed route on an old city road. Sure, the path might get crowded, but the route itself, completely fixed. Point A to point B every single time. But AI, man, AI is a whole different beast. It bends, it twists, it alters its path depending on prompts, the surrounding context, its training data, even incredibly slight changes in how you phrase something. You just can't ask, hey, did it work this one time? You have to figure out how it behaves across a wild, chaotic variety of situations.
And I want you to really keep this core idea in the back of your mind as we go through the rest of this explainer. Testing AI is way less like checking the math on a calculator, and it's much more like testing a human driver under rapidly changing road conditions. You're not just sitting there asking, does it answer the question? No, you're asking, when does it break? How badly does it break? And in what direction does it fail?
Which brings us to proving behavior over outputs, the rules of evidence. Let's quickly establish exactly what an AI test actually has to prove to be considered valid evidence of a system's true tendencies.
These 6 core principles right here, this is our foundation. When you put these together, they prove that a strong AI test is a deliberate claim about behavior under very specific conditions, not just a random snapshot of a success. You've got to clearly define what good actually means, expose true behavioral patterns, and crucially, connect those patterns to tangible risks. The test has to represent the messy, real world. It has to give you actionable insights. And maybe most importantly, it absolutely needs to make sense to the PMs, the engineers, and the policy teams you are working with.
Here's the thing you really need to take away from this. Your standard for good has to be precise enough to actually mean something, but flexible enough to reflect real-world usefulness. Traditional code demands exact match returns, but AI behavior, it's a lot softer. You really should judge it almost like a teacher grading a school essay. You're asking, is it clear? Is it relevant? Is it fundamentally accurate? You're not hunting for robotic exact match wording. You're looking for that underlying quality.
I absolutely love this analogy because it perfectly nails the trap we all fall into. Tasting one single spoonful of soup tells you literally nothing about the rest of the pot. If your test is just taking one spoonful, one prompt, you have zero idea if the system is consistently seasoned. Like, would it still pass if the user gave way less context? What about weird edge cases? Your tests need to dig up true behavioral patterns, not just accidental, one-off culinary successes. Because look, not all mistakes matter equally. Think of it like inspecting a bridge. You aren't just looking to see if the pavement is nice and smooth. You're down there inspecting the load-bearing joints, where a failure would actually cause a massive disaster. A minor inaccuracy from an AI might just be annoying, but misleading confidence? Wow, that causes immense trust damage. Unsafe content? That creates actual real-world harm. A truly strong test focuses its attention exactly where the consequences are the absolute highest. Moving on to designing controlled friction. We're testing in the gaps where certainty drops, and we're going to turn our tests into highly sensitive weakness detectors.
The absolute best tests create what we call controlled friction. That's just enough pressure to expose if the system is actually robust. By tweaking the wording slightly, changing up the amount of context, or throwing in distracting, conflicting details, we're basically testing the AI like a key in a lock. A fragile key is only going to work when it's perfectly aligned, but a strong, well-made key, it works even when the angle is slightly off. If you vary just one little element and the AI's behavior swings wildly, bingo, you've just found a critical sensitivity.
It is super vital to remember here that AI weakness is incredibly subtle, and it often wears a disguise. In normal software, an error is obvious, right? It crashes, it throws a 404, it times out. But an AI that sort of answers the prompt or totally misses the actual intent while sounding incredibly fluent and confident, that is still highly, highly fragile. And honestly, it's way more dangerous precisely because it hides right behind all that confidence.
This right here is the difference between the amateurs and the experts. Designing tests around specific points of collapse is going to give you far sharper insights than just checking off broad task labels. Labeling a test something generic like summarization is kind of like a mechanic looking at a car and saying, well, it drives. Sure, okay, but what brakes under stress? Do the brakes fail on a wet road? Does the steering lock up on a sharp turn? You have to test the failure mode, not just the overarching task.
Diagnosing the exact layer of a weakness is what actually drives your next actionable decision. If a model fails, you can't just slap a bad label on it and call it a day. Why did it fail? If it answers the wrong question entirely, well, that's an understanding failure. If it conflicts with itself halfway through the response, that's a reasoning failure. Pinpointing that exact layer tells you exactly whether you need better prompt framing, multi-step checks, or way stricter guardrails.
So the real gold here isn't found in one single sample, but in the contrast between samples. Creating these near-neighbor cases, which are basically inputs that are similar enough to compare, but just different enough to expose sensitivity, is how you see the system's true shape. For instance, try comparing how a customer support model handles a super clear question about tracking an order versus a slightly vague, frustrated query that has conflicting payment details in it. That contrast is going to reveal the exact boundaries of what that AI can actually handle.
And that brings us to the cartographer of brittleness, mapping where the system bends. It's time for the ultimate paradigm shift in how we approach this. We're stepping fully into your new identity as an AI test designer.
Here is the core mental shift you need to make. A beginner looks at a response and asks, is it right? But an expert, which is what we are now, asks, how stable is this behavior and exactly what kind of pressure breaks it? When you make that mental shift, testing literally transforms into cartography. You are actively drawing a map of where the system is strong, where it is highly sensitive, and where it is fundamentally unsafe. You're a diagnostician now. You're not just someone checking off boxes on a clipboard.
I want to leave you with this final, provocative thought to chew on. You've stopped admiring lucky outputs. You've learned how to apply controlled friction, expose those hidden failure modes, and actually map the exact points where the system bends under pressure. So, now that you can clearly see where the AI is brittle, how will you use that evidence to decide if the system is truly safe to trust in the real world?